Heap sort. Heap sort is a comparison based sorting algorithm that uses heap data structure in order to sort an array. This algorithm is going to be based on how heap data structure functions, and we'll be using those functionalities in order to sort our array. So in case you are not aware of heap data structure, or if you don't know the functionalities of heap, then don't worry, you have two options. You make the right choice according to whatever is your present situation. Okay, I'll put both the options before you. The first option is, in case you are a long-term algorithm student, or if you want to have crystal clear idea on how exactly heap works, what exactly are its functionalities and what we are using here, in that case you should first go to a heap lectures under data structures lecture series. So once you do that, the whole heap concept will be crystal clear for you, and then if you are coming back to this lecture will be a cakewalk for you. That is the first case. Otherwise, if you are here just for heap sort, or if you have algorithms exam tomorrow and you just want to prepare for that examination, if that is the case, then you can continue with this lecture. What we'll do is, whenever we want the heap concepts, we'll just touch upon the basics of those concepts so that you understand heap sort and you are in a good position to write heap sort algorithm. Okay, so you make the right choice among whichever this is applicable for you. Let us start with heap sort. So the idea behind heap sort is this. First thing is that you will build a max heap from the array that you have. You are having an unsorted array. From that you will be building a max heap. So the reason is, heap is already a complete binary tree. So because heap is already a complete binary tree, you generally represent heap by an array only. So you generally use array representation for heap. What are you having? You are having an unsorted array. So you can consider that unsorted array as a complete binary tree, and you can convert it into a heap. So the whole data will be residing inside your array itself, and you can visualize it like a heap. Okay, so this is your heap. Think this is the heap from your array. What is the speciality of max heap? Max heap will always have the largest element as the root. This is the speciality of a max heap. So now that your array is a max heap, whatever is the largest element would be placed at the root. We are going to use this property of max heap in order to sort. So by this point, you can have somewhat a guess of what we are going to do. We are having an array. We know the root, which is the first element, will be the largest element once we apply max heapify. So once it is a max heap, what will you do? You will exchange, this is the largest element right now. You will exchange this largest element with the last element. What happens now? This largest element will come here. Whatever was here, that would go to the root. And in this case, you know, whichever is the last element of array, that will be the largest element, because you are making the last element as the largest. What is the next step? You will just consider that this element is not a part of heap. You will only consider this much part of array. And you will repeat the same process. You will again heapify, make it a heap. When you make it a heap, what happens? Whatever is the largest element, that will come to the root. Then you will exchange root with the last element. Now what happens? Second largest element will reach this position. After this, you will just consider that this element is also not present. So in your array, you will only consider this much. From this, you will again heapify. What happens? Whatever is at root, that will become the largest element. So the largest element will be pushed to the root. You know this is the from whatever is remaining, this is the largest element. What will you do? You will exchange this with the last element. So again, third largest element will come here. Similarly, you will keep filling, and by the end you will have complete array sorted, because you want to sort in ascending order. First element should be least, last element should be largest. So this is how we'll be using heap data structure in order to sort our array. What we'll do now, we'll take numbers and then we'll dry run so that you'll understand clearly how this algorithm is going to work practically. Okay, so again, as we did in all our previous lectures, we'll be taking same set of numbers so that you clearly understand how these numbers are manipulated. Okay, I want you to understand what is the difference in manipulations in different sorting algorithms. That's why I'm using same set of numbers. Okay, so this is the array that you have: 42, 70, 12, 30, 24. This is the array that you have. This is the unsorted array, and you want to sort this array. How will this look as a complete binary tree? As a complete binary tree, 42 will be on root. Then you will have 70 and 12 as its children. 70 will have two children, 30 and 24. This is how it will look as a complete binary tree. The next thing is you have to make this a heap. So from this unsorted array, you want to build a heap. So when you build a heap, what do? You start from the last non-leaf element. You apply heapify on it. That is, you check both the children of this particular node. Then you will see whichever is the largest. So if root is the largest, that is, here you are considering this node. If this node itself is the largest, nothing to be done. If it is not the largest, you have to swap it with whichever is the largest child. Okay, and you want to recursively do this till you reach a leaf, or you reach a position where the present node is the largest. That is, whatever is your root under consideration, when that is the largest, you can stop. Otherwise, you should continue this recursively till the point you reach the leaf. So at this point, 70 is already largest, so you don't have to do anything. Then you reach 42. When you are considering 42, 42 is not the largest. 70 is larger than 42, so you will swap. 70 will come here, 42 will come down. Again, you will check 42 with 30 and 24. 42 is larger, so nothing to be done. So your heap is this. This is the heap that you built from this array. So after you built the heap from array, how will your array look like? Your array will have 70 here. Then you have 42 here. The remaining are same: 12, 30, 24. So this is how your array will look after you built the heap. So presently this is a heap. It is not just an array, it is a heap. What is the speciality of heap? Whatever is the largest element, that will be at the root. So I'm going to draw the heap again according to the new set of elements. 70 is the root. Then I have 42 and 12 as the children of 70. Then I have 30 and 24 as children of 42. What should I do now? I should swap the root with the last node, whatever it is. So I'll swap 70 with 24. 24 will come here. 70 will come here. So what should I do? I should have, in the array, I should do the same operation, right? I'll swap 70 with 24. So 24 will come here. 70 will go to the last element. What will I do now? Next step is I will consider that 70 is not part of my array. I'll remove 70 from the heap. So 70 is already sorted. 70 is the largest element. This much is already sorted. In the next iteration, I am only going to consider the remaining elements for my heap. So now my heap is only having these much elements, and it has already violated the heap property because I swapped 24 and 70. Because of that, there is a heap property violation. What do I have to do now? I have to heapify again so as to restore heap property. So I'll heapify starting from 24. What happens? I'll compare 24 with 42 and 12, which are its children. 42 is larger, so I'll swap. 42 will go on top. 24 will come down. Again, I'll check 24 with its child, which is 30. What happens? 30 is larger, so I again have to swap. 30 will go up. 24 will come down. So this change, I have to make it reflect in the array. So this will be 42. Next is 30. Next is 12. Last is 24. So this is my heap. Presently, this is a heap. So last element, that is separated. Remaining part is a heap. So this much of array is a heap. What is my next step? I have to exchange the root with the last element. Last element is again 24, right? So I have to exchange it with the root. What happens then? If I exchange last element with 24, 24 will come on top. 42 will go as the last element. So I have to make the corresponding change in the array as well. 24 will come here. 42 became the last element. What is the next step? I need to isolate 42 as well. So I'll consider 42 not a part of heap. So this much is not a part of heap because I know the last two elements are already sorted as per heap sort algorithm. So presently my heap is only having three elements, 24, 30 and 12. And is the heap property followed? No, the heap property is not followed because it got violated when I swapped the root with the last element. 24 was the last element. I swapped it with the root. So what do I have to do? I have to heapify again. How will I heapify? I'll compare 24 with both its children 30 and 12. Which is larger? 30 is larger, which means I have to swap 24 with 30. So 24 will come here, 30 will go up. So this is my heap and I have to make the same changes in the array so that whatever change I made here is reflected in the array. So in my array, 30 will come here, 24 will come here. So see, whatever changes I'm making in the array, when we do it in a program or in the algorithm, whatever changes I'm showing here in a picturized manner, this will actually be done in array only. So you don't have to specifically go to array and repeat those changes. Here I'm repeating again in the array because I am doing it separately in a picture kind of manner so that you understand it is a heap and you clearly understand what are the manipulations I am doing. So that is why I am having to again do this on the array. Actually, when you are writing the algorithm or you are actually coding it down, you will be directly doing everything on array itself because heap is having array representation. So you will be using array as a heap. You are not going to have a special picture for heap. Okay. So this is your heap right now, 30, 24, 12. This is how it will look as a heap. What is the next step? You have to swap your root with the last element. What is your last element? 12 is the last element. So what happens then? 12 will come on top, 30 will go down. So 12 will come here, 30 will come here. What is the present situation? 30, which is the largest element, I have already swapped it to the end. Next step is I'll consider that last element, which is 30, is also not part of the heap. So this much is last three elements are not part of the heap for me now. Heap only has 12 and 24 remaining. I'll consider that all these are not part of the heap. What is the present situation? Is the heap property followed? No, the heap property is violated. Why is it violated? Because I swapped 12. So whenever I do the swap, heap property gets violated. I have to heapify again. When I heapify again, what happens? 12 and 24. If I heapify them, 24 is larger than 12. So 24 should come on top and 12 will be in the bottom. What is the next step? So this heapify, I'm showing it in the array as well. 24 will come here, 12 will go down. After this, I again have to swap whatever is the root with the last element, which is 12. 12 is the last element now. So I'll swap 24 and 12. So 12 will come on top, 24 will go down. So 12 will come on top, 24 will go down. What is the next step? I'll consider that last element, which is 24, is not part of the heap. So I'll consider 24 also not part of the heap. So at this point, only one element is remaining in the heap. And one element is by default sorted. There is nothing to be compared. So you're already done with complete array. And you can see that your complete array is sorted now. So this is how you sort an array using heap sort algorithm. What we are going to do now is we'll write the pseudocode for this algorithm and then let us see what are the time and space complexities of heap sort algorithm. Let us write the pseudocode. So while writing pseudocode, what are the things you should have in mind? You should have the logic clear. In the logic, what do you want to do? First thing is you want to build a heap from the unsorted array. After you build a heap, what should you do? For each of those, for each of the element, you have to eliminate them one by one. How do you eliminate? You would find the largest element each time. So presently you build a heap. So first step is you want to build a heap. After building heap, what should you do? You should run a loop And in that loop, you should select the largest element in the heap, which is the root element, place it at the end of the array, again heapify, again take the largest element, place at the end of the array, again heapify, and so on. So this is what we are going to write in the pseudocode, okay? So let us start with the pseudocode. You are going to write heap sort algorithm. So heap sort of, let us say, array A. A is my array, okay? A is the unsorted array which I want to sort using heap sort. What variables should I have? First thing is I should have something to keep track of length. So n, let us say, n is equal to length of A. So n is where I am tracking length of my array. What is the first step? I want to build a heap. So for building a heap, what is the procedure? I have to go to the last non-leaf node, and from there I have to apply heapify. Then I have to do on second last non-leaf node. Again I have to apply heapify. I'll go to third last non-leaf node. This is the process for building a heap from unsorted array, okay? So for that I'll have a for loop for I is equal to, which is the last non-leaf node. Last non-leaf node in a heap is the node which is positioned at n by 2 minus 1th position. Whichever node is at the position n by 2 minus 1. How will you find it? In the array you are having indices. So 0, 1, 2 up to n. So whichever is the index at n by 2 minus 1. So you have to choose the index n by 2 minus 1. That will be your your last non-leaf node, okay? So I is equal to n by 2 minus 1, and you have to take floor, okay? 2 up to 0. So from this you have to go in reverse level order till 0. So I'll just show you an example so that you understand this. 0, 1, 2, 3, 4, 5. If these are the nodes that you have in the tree, and if you want to find whichever is the last non-leaf node, what will you do? N by 2 minus 1. N is 5. N is 6. So if you do n by 2, you will get 6 by 2 is 3. What is 3 minus 1? 3 minus 1 is 2. So what is the last non-leaf node? 2, right? So that is how you find the last non-leaf node. And from there, you have to go till 0, which is the root. So what will you do? In each of those, you have to do heapify procedure. So heapify procedure, we'll write that algorithm after this. For now, we'll just write heapify, okay? Heapify of array A, which is of size n, to be heapified at position I, okay? So A is your array, which you're considering as the heap, and that array is of size n, and you want to apply heapify procedure at the node I. This is what this means. We'll write heapify procedure after this, okay? So when you do this, your heap is built. This is the first step. After this, so this is exactly what we did with the tree that we initially did with when we were sorting using heap sort, okay? Next step is I have to do the swapping part. That is, I have to select the largest element, put it to the last of array, again heapify, select the largest, put it to the last available position, again heapify. This is what I'm going to do now. For that, I have to write a loop. So for that, for I is equal to n minus 1 to 1. So there is a reason why I'm starting from n minus 1 to 1 instead of going from 1 to n minus 1. So you'll understand this now. The reason is, see, what do I have to do? I have to swap root with the last element. What is the last element in an array? In an array, see, this heap will be represented as an array. So from index 0, it will start. Then you have 1, 2, up to n minus 1. See, you are having n elements in total, which means last index will be n minus 1. So in the first step, in the first iteration, what do you have to do? You have to swap the root, which is at index 0, with the element at last, which is at index n minus 1. So if I iterate from n minus 1 to 1, what is the benefit that I'll get? In the first iteration, I can swap 0 with whatever is the value of I, that is n minus 1. And in the second iteration, I will have to again swap 0 with what? N minus 2. So automatically value of I will be n minus 2 in the second iteration till the point I reach 1. So by the time I do 1, all the elements will be sorted. So this is the logic. What do I have to do now? Given that I'm already having a heap, I have to swap the root with the last element. So I will do swap. What is root? Array of 0. Whatever is at root, I'll swap it with last element a of I, right? So this last element, as we already said, we'll consider that the size of heap is decreasing after each iteration. So last element will be n minus 1th element for the first iteration. But for second iteration, last element will be n minus 2th element, because we'll be considering that the heap size is decreasing by 1 after each iteration. So after swapping the root with the last element, what will you do? You again have to heapify, right? You have to heapify. But there is a catch. In this heapify, what are you going to do? There is a catch here. You are not going to apply the same heapify to array A with a size of n at position I. That is not what we are going to do. This time at array A of size I at position 0. Why is it? Because size is I. So initially size of array was n. But when we enter first loop, we want to eliminate one element now. So we'll consider size as n minus 1. So when we enter this first iteration, value of I will be n minus 1. We are using that value of I here. That is why we iterated from n minus 1 to I. One reason is for swapping. Second reason is for this heapify. Here you can directly use I. What happens in second iteration? Value of I will be n minus 2. So you will consider size of heap as n minus 2 in second iteration. And what is the third argument? This is the position at which you want to apply heapify. So where will you apply heapify? At whichever position you disturb the heap structure. So here you are disturbing at the root, because you are swapping the element at root. So basically the disturbance that you are causing to the heap is at root. That is why you are applying heapify at root. So this is the heap sort algorithm. Okay. Next heapify algorithm we'll write right now. So heap sort algorithm is this. Initially you are having the length of array. Then you are having one loop in order to build the initial heap from sorted array. Okay. For that, what will you do? You will run this from the last non-leaf node till the root. You will continuously apply heapify. So this will build a heap from unsorted array. So after this, what will you do? After this, you will go from n minus 1 to 1. For each of the iteration, what will you do? You will swap the root with the last element and heapify again with size 1 less. Whatever was the size of your previous heap, you will be having a heap with 1 lesser size. Okay. Next, we'll see the heapify algorithm. Then it will be clear for you how it works together. Okay. In the heapify algorithm, what are we going to do? In the heapify algorithm, the core part is we want to heapify. That is, whatever heap property was violated, you want to rebuild a heap so that whatever structure you are having is maintaining the heap properties. So that is what is heapify procedure. So see again, for heapify or build heap, whatever, if you want a detailed explanation, please go to the corresponding heapify lecture, build heap lecture, and so on from data structure series. Here we are just going through all this so that you have a clarity on what all to be done. Okay. Heapify. What is the heapify algorithm? Heapify algorithm to be applied on array A of size n at point at the index I. So how do you do this heapify? This is what we are going to learn now. What does this procedure mean to be? This procedure means you disturbed the heap property at position I. What do you want to do? Because you disturbed heap property at position I in the heap, you will apply heapify at position I so that this complete heap again regains the property of heap. But there are certain conditions for applying heapify. The left subtree, that should already be a heap. The right subtree, that should already be a heap. And the only violation should be at the root or whichever node you are applying. So below that, whatever you are having, all of those should be a heap. Then if you apply heapify here, this whole thing, this whole subtree, whatever you are looking at, this will become a heap. This is the heapify process. Okay, so that is what we are going to apply. Let us see how to heapify. So the first thing is that in heapify, what is the procedure? You want to check whether the parent is larger or if any of the children are having larger values. If the children are having larger values, you will swap parent with whichever is the larger child and then recursively continue on that particular child. The same process. You will consider that child and its children. If its children are larger, you again continue this, or if that child is larger, then you will stop here. Whenever you see that the value of root is larger than both its children, if value of any parent, if that is larger than both its children, at that point you can stop your heapify process. So here we are going to write iterative algorithm so as to be better with space complexity. So first of all, we'll define what variables we need. One is always you want to track what is the largest. So because we are applying heapify from ith node, we'll initially consider that the largest value is at node I. Okay, this is the assumption we are making. Next thing is we'll start a loop. So this loop is while 1 means continue this loop until some break condition. We'll do that break inside this loop. That is what we are going to do. First thing is, what all variables will we need? We'll need a left child, we'll need a right child. So how do you identify left child? Left child, if you have a heap, if you want to identify the left child, you can use the formula 2i plus 1. So that will be the left child of node I. Okay, so presently you are looking at node I. Its left child will be at 2i plus 1. Similarly, how do you find the right child? Right child will be available at 2i plus 2. So these all come under heap properties. In a heap, if you have any node I, left child can be found at 2i plus 1th index. Similarly, right child will be at 2i plus 2. So this come under heap properties. Once you have these indices, what is the next thing? You want to check whether the left child is larger than the parent. How do you check whether left child is larger than the parent? You'll put an if condition. If, first thing, whether you have to verify whether this index exists or not, because I exists doesn't mean always 2i plus 1 exists. Maybe that is out of index. So first you have to confirm that this exists. So what will you do? Left less than n, you'll put this condition. So n is the total size of array. So this index, whatever it be, should not go beyond the array. If it goes beyond the array, that means that particular child is not present. Okay, you can stop there. So left less than n. And what is the second condition? You want to check whether the left child is larger than whatever is your present largest. So presently you are considering I as largest. So second condition is a of your left child, a of left, if this is larger than a of largest. So you have index largest here. This index is always supposed to carry the index of the largest element among considered elements. So here you are checking that presently whatever is your largest. So presently I is your largest. That is your assumption. If left child is having a larger value than that, then what will you do? You have to update this largest. So if this condition satisfies, what will you do? You'll update largest is equal to left. This is the updation you have to do. What is the second check you have to do? You have to make the same check for the right child. So in case this hits, then what happens? Largest will hold left child's value, left child's index. If this condition doesn't hit, then largest will hold parent node's index. So whatever it be, largest, that variable will be holding the index of whichever is the larger one among parent and left child till this point. So we'll put same condition for right child as well. If right is less than n, and what is the second condition? Array of right is greater than array of largest. If both these conditions satisfy, that means whatever is your right child, if that is larger than left child and larger than your parent, if right child is the largest, then your largest variable will be updated to right. So at this point, what you have, whatever is stored in your largest variable at this point, that will be the largest value among parent and both its children, left child and right child. So you largest will store the index of whichever is the largest. So what should you do now? You should know whether you should do a swap of the parent or not. When do you want to do a swap of the parent? You want to swap the parent with its children, either of its children, if parent is not the largest. If parent is already largest, you can stop there. You are done. In case parent is not the largest, you have to swap the parent with whichever child is largest. So what will you do now? If largest is not equal to I. See, if largest is equal to I, you are done. You don't have to do anything because parent is largest. It is already following heap properties. If parent is not largest, what should you do? You have to swap. You have to swap A of I, that is parent, with A of largest, whichever is the largest child. With that, you'll be swapping parent. After swapping, what should you do? You should make I is equal to largest. That is, in case you do a swapping, you want to recursively continue this heapify process in all the children. Not all the children, whichever child you did the swap with. In that, you have to recursively continue the heapify process. Because here we are using an iterative process and we put a while loop with a condition of 1. That is, here we have a while loop which is having condition 1, which means it will keep iterating. So instead of recursion, what we did is we put an infinite while loop. In that, if I is updated as largest, what will happen in the next loop? Next loop, it will do the same process for whatever is the new I. So new I is the child which was largest. In that position, you swapped and then you are having that position to be executed. In that position, you will execute heapify procedure. I equal to largest, and if this is not the case, if largest is not equal to I, what should you do? You will hit else case. If you hit this else case, then you should break. Why should you break? Because you are having an infinite while loop. So this while loop will exit only if you are breaking here. So if there comes a case where parent is the largest, that is largest is not either of the children, but it is I, which is the parent itself, then this loop will break here. So this is when your heapify loop will come out. So this is your complete heapify process. Let us just understand the whole process once. In the heap sort procedure, what did you do? You initially had the length, then you built the heap here. After building the heap, what did you do? For each of the iteration, you took the root and you placed that root at the end of the array. Then the question is, how exactly did you place that root at the end of the array? That is after placing root at the end of the array, that is placing is swapping. After placing, how did you re-heapify? How did you regain the heap properties? That is heapify procedure. So that regaining of heapify properties, that is done here in the heapify procedure. What did you do here? You initially assumed that parent is the largest. Then you went into a loop where you identified both the left and right child of the parent. If left child is existing and it is larger than parent, you will say till this point larger is the left child. Then you will check the right child as well. If right child is existing and right child is larger than whatever is the largest till this point, that is whether it be parent or left child, then you will update largest to right child, which means right child is the largest among all parent, left and right. Then you will have a check whether the largest is parent or if it is any of the children. So in case largest is not parent, it means it is either of the children. So in that case, you will swap parent with whichever is the larger child, and then you will update the value of I to that node, largest node. That means in the next iteration, the same process will be done for that child with whichever you did the swapping. After that, the other thing is, in case parent itself is the largest, you will break from this loop. So this is the breaking condition. Next question is, what are the time and space complexities of this algorithm? So first thing you have to understand here is, there is a reason why we used iteration here. We could easily have used recursion, but we purposefully used iteration so that space complexity comes down. So because of iteration usage, space complexity is order of 1. Okay. Ideally, space complexity would have been order of log n if we used recursive procedure for heapify. So in that case, what happens? Heapify will be recursively called as per the height of the heap, and the maximum height of a heap is order of log n. So if you use recursive procedure for heapify, then space complexity will be order of log n. Here we intentionally used iterative procedure so that space complexity comes to order of 1, because you are not having any recursion stack here. You can see this. And the only usage is the variables that we are using, which is constant, left, right, I, and so on. Those are constant spaces. So because of a iterative strategy, space complexity of a algorithm is, heap sort algorithm is order of 1. What about time complexity? So here you have to be careful. If you are using recursive strategy, space complexity will go to order of log n. Here, because of iteration, space complexity is order of n. So I'll just note here order of log n if recursion. Okay, in case of recursion. Here in case of iteration, it is order of 1. What about the time complexity? How do you analyze the time complexity here? What all are you doing here? First thing is build heap. So build heap is this. When you are building heap, what is the time complexity? It is order of n. Why is it order of n? So exact explanation of why build heap is order of n, you have to refer to the build heap lecture, because it will waste time here. Just understand that build heap time complexity is order of n. We had explained it in detail in build heap lecture. So this part is having order of n time complexity. Okay, that is first part. Next part is your heapify procedure. Heapify procedure, this is going to take order of log n time. Heapify will take order of log n time. Secondly, you have to extract element. That is, once you do heapify, you will extract element. So extracting element, that will take order of, okay, you can leave that order of log n. And overall, what happens? Because you are doing this heapify with order of log n, how many times are you going to do this? You are going to do this order of n times, right? Because you want to remove the root and again reheapify n times, because that is how you are going to construct your complete sorted array. Each time you will remove root, then again reheapify this complete array. Remove root, reheapify this complete array. Again you will remove root, reheapify this complete array. So what happens? Order of n times you have to do reheapify for order of log n. So order of n into order of log n means your total time complexity will be order of n log n. So this is the total time complexity of heap sort. So for heap sort, time complexity is order of n log n, space complexity is order of 1 considering iteration, order of log n if you are using recursion. Next thing is this a stable sort, and is it in place? So first thing is, it is an in place algorithm. Heap